Okay, this is part 7 of our section on section 3.4. This, I'm assuming, is basically for Wednesday's class. So this is a big section, section 3.4 is. So I was anticipating it would take about a day and a half. So don't panic if you're like, I'm still in the middle of just one section. You're on Wednesday's material. Okay, so we had a lot of theory and we really just worked through one example. So I just wanted to do another example. And with this example, I'm going to encourage you periodically to just pause the video, do a step, and then turn it back on and check with my work. Okay? All right, so we're looking at this system. Y prime equals this matrix A, real valued, times Y. Okay? And I want to try to find all of the solutions. So I'm going to first of all find the general solution. And of course, that's looking in the real numbers. If I wanted, I will find a complex solution if I need to, but I want to find the general solution, and then I want to sketch the phase portrait. Okay, so the first thing I'm going to do is I'm going to try to find the eigenvalues for this matrix. So I would encourage you to pause the video, find the eigenvalues, then turn it back on and check your work. So will you take a moment to pause? I shall impersonate an equilibrium solution. Welcome back. Okay, so if this was A, I'm looking for A minus lambda I, which would be the matrix I get if I subtract lambda from the main diagonal. So that's going to be 2 minus lambda, 1, negative 2, negative lambda. Okay, that's that matrix. I'm going to now take the determinant of A minus lambda I. So that's going to be 2 minus lambda times negative lambda. Minus a negative 2 is going to be a plus 2. And my characteristic equation is when I set that equal to 0. The roots of this equation will be my eigenvalues. So let's work that out. If I distribute that negative lambda, I'm going to get a lambda squared. Looks like a minus 2 lambda, and then plus 2 is equal to 0. So that doesn't look like it factors. Let's use the quadratic formula. So lambda is going to be the opposite of b, will be positive 2, plus or minus the square root of b squared is 4, minus 4 times 1 times 2, that's 4ac, all over 2a is 2. So that's 2 plus or minus the square root of 4 minus 8 is negative 4 over 2. That is 2 plus or minus 2i all over 2. I can factor out a 2 here and then cancel. So that's 2 times 1 plus or minus I all over 2. Those cancel. And so I'm going to get 1 plus or minus I. So hopefully that's what you got for your eigenvalues. Okay. So now our next step is going to be to find an eigenvector. Okay. I'm going to suggest that while I'm erasing the board, you take a moment to pause the video and try to find them, but let's agree what we're going to do. Last time I purposely chose the one with the negative imaginary part. The advantage of that is when I subtract it from A, it becomes positive. The drawback is then a negative number shows up in the argument for my trig functions. So this time I'm going to choose lambda 1 to be 1 plus I, and I'm going to try to find an eigenvector. So again, go ahead and pause the video. I will erase the board, then come back, see if we get the same eigenvector. Okay, so in looking for my eigenvector, I'm looking to solve A minus lambda I times some vector v, whose components I'm going to write as v1, v2, equals 0. So A minus lambda I, I'm subtracting this from the main diagonal. So I'll have 2 minus 1 is 1, minus I, don't forget I'm distributing that negative. Okay, then we have 1 and negative 2. And then in the lower right-hand corner, negative 1 minus I. We're looking at times v1, v2 equals 0, 0. So that gives me this lovely system of equations. 1 minus I times v1 plus v2 equals 0, and negative 2v1 plus a negative 1 minus I times v2 is equal to 0. Again, when we're working in the complex numbers, it's not super obvious that this is a dependent system. I don't just look at that and say, clearly the second equation is a multiple of the first. But I know that it is, because I know that 1 plus I was an eigenvalue. So that means I really just need to solve one of these. So I'm going to take this equation, and I'm going to solve it for v2. So v2 is just negative 1 plus I copies of v1. So that's a negative 1 plus I, because I'm moving this over to the other side. Okay. Excellent. So I'm going to choose for my eigenvector v, I'm going to call it v1 just to make it go with lambda 1, but I'm only finding one of them. So if I just wanted to call it v, that would be totally fine. I'm going to choose to make v1 1, and that way v2 is just negative 1 plus I. Fabulous. We've got ourselves an eigenvector. So with this, we can form our complex solution. So I'm going to form my complex solution, and then I'm going to work it out and simplify it to try to get to the real and imaginary parts. Remember, those are my two independent, real-valued solutions, and then an arbitrary linear combination of them will be my general solution. So, again, I'm going to encourage you to pause the video and try to work that out on your own, and then turn it back on and rejoin me. Again, instead of impersonating an equilibrium solution, I'll take the time when you're pausing to just erase the board. Welcome back. Okay, so a complex solution is going to be e to the 1 plus I times t copies of this eigenvector, 1, negative 1 plus I. Now I can erase that again. I just had it up there so I wouldn't forget what it was. Okay, so I want to try to simplify this. So notice that's e to the t times e to the it, 1, negative 1 plus I. So that's e to the t times cosine t plus I sine t. Now here you see maybe the advantage of choosing the eigenvalue with the positive imaginary part is that my argument in sine and cosine doesn't involve a negative sign that I have to pull out. The advantage of choosing the one with the negative is that when I was subtracting it to form a minus lambda I, subtracting a negative, it became positive. So it's really just a matter of personal preference. Okay, so let's see, that's this part, and then I've still got to scale my eigenvector by that. Okay, so let's write out our eigenvector. That's going to be up here, e to the t cosine t plus I times e to the t sine t. That one's super nice because that's already in real part plus I times imaginary part. Here I'm going to need to distribute. So what I'm going to do is I'm going to distribute I'm going to actually keep the e to the t factored out and distribute the negative 1 and the I. So that's going to be e to the t times the negative 1 will give me a negative cosine of t minus I sine t. And then distributing the I will give me a plus I cosine t. And then plus I squared sine t. And of course, what is I squared? Why, yes, it is negative 1. So I can rewrite this. Means I'm just copying the first term because it's already in a form I like. But I'm going to have e to the t times, I'm going to just consolidate my real terms now. So that's the negative cosine t, that was real, and this becomes negative sine t. That's also real. So those two parts were my real part, and then plus I times these two parts being still multiplied by the e to the t. So I'm kind of doing two things here. I'm distributing the e to the t, and I'm consolidating the real and the imaginary parts. So for the imaginary part, we'll have e to the t distributed to these two pieces times I. So we're going to have a negative sine t plus cosine t. Excellent. So that is a complex solution. Now that means that I can find my real and my imaginary parts. So the real part is just the real part and the real part here. So that's e to the t cosine t, e to the t times negative cosine t minus sine t. The imaginary part is the imaginary part here. Remember, that's the real coefficients that get multiplied by I. The I is not actually part of the imaginary part. So it's e to the t sine t, e to the t times negative sine t plus cosine t. So my general solution is going to be a copies of the real part, e to the t cosine t, e to the t times negative cosine t minus sine t, plus b copies of the imaginary part, e to the t sine t, e to the t times negative sine t plus cosine t, where a and b are real numbers. Okay, so we have found our general solution. Now I also wanted to sketch the phase portrait, so I'm going to stop the video and make that the next video just so this video doesn't get too long. But the next video will pick up with this problem, finding our phase portrait.